Hello everyone and welcome back to the class. Today we will study another class of circuit which are formed by combination of passive element and are known as RL circuits. Now we will start the analysis of RL circuits, and these circuits are consist of resistor and an inductor. Like RC circuits, these circuits also have wide application in communication, electronics and control system. And for analysis of RL circuits, again Kirchoff laws are applicable here. Like Kirchoff laws were applicable in the case of resistive circuits and RC circuits. But the difference from resistive circuit is that applying Kirchoff laws to RL circuit will give us a first order differential equation. So these circuits are also known as first order circuits, like we were having in the case of RC circuits. The RL circuit can also be excited in two ways. In first case, it is assumed that the energy is initially stored in the storage element of the circuit, which can either be inductor or capacitor. And these are also known as source-free circuits. This stored energy in the storage element causes the current to flow and is dissipated in the resistor of the circuit. And these circuits are free from independent sources, but may have dependent sources. The second way of exciting RL circuit is with the help of independent sources. We have studied DC analysis and we know that for DC source, inductor act as a short circuit. So we will consider independent DC sources in this part of Electric Circuit Analysis 1 course. Now we will study analysis of source-free RL circuit given in the figure 1. The circuit consists of an inductor and a capacitor, and we have to determine response of the circuit, which in this case will be the current through the inductor, because we know that current through an inductor cannot change instantaneously, and we also assume that inductor was initially connected to a DC source and energy is stored in it, and the initial current stored in an inductor is represented by I0, and mathematically I of 0 equals I0. And the initially stored energy in an inductor will be omega of 0 equals half inductors of inductor multiplied by square of the initial current. Now for the response of this circuit, which is current through an inductor, we will apply KVL to the circuit in figure 1. And we will have a relation that sum of voltage across resistor and voltage across inductor will be equal to 0. And we know that voltage across inductor is equal to product of inductance of inductor with rate of change of current, where voltage across resistor is equal to product of current through the resistor and resistance of resistor. Now substituting these values and rearranging, we will have a relation di over dt plus R over Li equal to 0. Now to find response of inductor current, we will rearrange and perform integration of the equation di over I equals minus R over L dt. And after integration, we will have natural log of current with limits starting from initial current I0 to present current I of t, and will be equal to minus R over L t with integral limits of time 0 to present time t. Now substituting the integral limit and using the rules of natural log, we will have natural log of I of t over I0 equals minus RT over L. Now to find value of I of t, we will take power of exponential on both sides of equation, and this will give us I of t will equal to I0 multiplied by exponential power minus RT over L. And this equation 1 will represent natural response of an RL circuit, which in this case is equal to exponential decay of the initial current. And the natural response of an RL circuit is shown in the figure 2, where at time t equal to 0 we have initial current I0, and as time increases the current decays exponentially, as exponential with negative power is again a decaying function. Now from equation 1 and also from the figure 2, it is obvious that after the time of one time constant, the current has a value of 0.368 or 36.8% of the initial current. So for any RL circuit, time constant will be equal to inductance divided by resistance, or L over R. Here the time constant again used is tau, which is a lowercase Greek letter. Now we know that the time constant for a RL circuit is equal to L over R, so we can conclude the following: that the smaller the time constant of a circuit, the response of the circuit will decay more quickly, and for larger time constant, slower will be the rate of decay. At any rate, the response of the circuit decays to the less than 1% of its initial value, which means that it will reach to its final value after the time of 5 time constant. Now using time constant tau, the equation 1 can be written as the inductor current I of t will be equal to I naught multiplied by exponential of minus t divided by tau. Now using equation 3, the voltage across resistor will be equal to product of current through the resistor with resistance of resistor and will be equal to I naught R exponential power minus t divided by tau. And the power dissipation in the resistor will be equal to product of voltage across resistor and current through the resistor and will have value of I naught square R exponential power minus 2t divided by tau. Now assume that at time t equal to 0, the circuit was disconnected from an independent DC source, so the energy absorbed by resistor from time t equals to 0 to present time t will be integral of power, and for integral purpose, the integral variable is changed from time to lambda. Now substituting the value of power and taking out the constant from the integration process, we will have energy of half lambda I naught square 1 minus exponential power minus 2t divided by tau. Now as the time approaches infinity, the exponential term in the relation of energy will approaches to 0, and the energy stored will be equal to half inductance of inductor multiplied by square of initial current, which is the same as energy stored in the inductor. So the energy initially stored in the inductor is dissipated in the resistor. During the analysis of source-free RL circuit, you have to keep two things in mind. First of all, you must have information related to initial current stored in an inductor, which is represented by I naught, and the time constant of the circuit. Using these two quantities, you can easily find current through the inductor, which will be equal to I naught multiplied by exponential of minus t over tau, where tau is a time constant. And once you know the inductor current, you can easily find voltage of inductor, resistor voltage, and resistor current. Whenever the circuit have a single inductor, several resistor, and a dependent sources, in that case, to perform the analysis of source-free RL circuit, which consists of a single resistor and single inductor, you can use Thevenin equivalent circuits. And you can find Thevenin equivalent at the terminals of inductor, which will transform given circuit into a simple source-free RL circuit. And in general, using equation 2, R will be replaced by a Thevenin resistor or equivalent resistor. Now in the given example, for the circuit in figure 3, assume that initial current across inductor is of 10 amperes and you have to calculate I of t, which is current through resistor, and Ix of t, which is current through 2 ohm resistor. Now the given circuit have two resistors, one inductor, and one dependent voltage source. This circuit can be solved by two methods. First one is to obtain Thevenin equivalent circuit at the terminals of inductor and then to find current through inductor with the help of equation 3, or the other way is using Kirchoff's voltage law. Now whichever approach is taken, it's always better to first obtain the inductor current. Now we will find inductor current with the help of method 1, which is to find Thevenin equivalent at the terminals of inductor. Now due to the dependent source, first of all we will insert a voltage source V0 of value equals 1 volt at the terminals of inductor, which are represented by A to B, as shown in the figure 4. Now to find equivalent resistance at the terminals AB, we will try to find out current I0, and for this purpose we will use mesh analysis and assign mesh currents of I1 and I2 to both loops. Now loop 1 equation will be 2 into I1 minus I2 plus 1 equal to 0, or I1 minus I2 will be equal to minus half. For loop 2 equation will be minus 2I1 plus 6I2 minus 3I1 equal to 0, which will give I2 equals 5 over 6I1. Solving this equation we will have I1 equal to minus 3 amperes, and we know that I1 and I0 both are in opposite direction, so I0 will be equal to minus I1, which will give us a value of 3 amperes. Now using Ohm's law, we will find the R equivalent or R Thevenin at the terminals A to B, which will be equal to V0 divided by I0 and will have value of 1 over 3 ohms. Now we will find time constant, which is inductance divided by R equivalent. Substituting the values of inductance and R equivalent, the time constant will be equal to 1.5 seconds or 3 over 2 seconds. So the current through inductor will be I of t equals I0 exponential power minus t over tau, and substituting the values we will have 10 into exponential power minus 2t divided by 3 amperes for time t greater than 0. Now second method to determine current through inductor is Kirchoff's law. Now for applying KVL, first of all we will assign currents, which will be I1 and I2, and the loop 1 equation will be half di1 over dt plus 2 into I1 minus I2 equal to 0, and solving this will give di1 over dt plus 4 into I1 minus I2 equal to 0. Now for loop 2, minus 2I1 plus 6I2 minus 3I1 will be 0, which implies that I2 will be equal to 5 over 6I1. Substituting and solving, we will have di1 over I1 will be equal to minus 2 over 3 dt. Since I is equal to I1, so we can replace I1 by I and will perform integration. So natural log of I with limits current at time t equal to 0 to present time t will be equal to minus 2 over 3t from time t equals to 0 to present time t. And applying the rules of natural log, we will have natural log of I of t divided by I of 0 will be equal to minus 2 over 3t. Now taking powers of exponential to both sides, we will have I of t equals 10 into exponential power minus 2t divided by 3 amperes for time t greater than 0, which is the same current obtained by method 1. As we have value of current through an inductor, so we can easily find other circuit variables. Now the voltage across inductor is equal to inductance of inductor in product with rate of change of current. Now substituting the values, we will have voltage of minus 10 over 3 multiplied by exponential power minus 2t divided by 3 volts. And as both inductors and 2 ohm resistor are parallel, so both will have same voltage. So the current Ix will be equal to V divided by 2 and will have value of minus 1.6667 exponential power minus 2t divided by 3 amperes for time t greater than 0. Now in the next example, for the circuit in figure 6, the switch was closed for a long time and is being open at time t equals to 0. Now you have to calculate current I of t for time t greater than 0. If you look at figure 6, the circuit consists of one inductor, 4 resistors and one independent DC voltage source. For time t less than 0, the switch is closed and inductor will act as a short circuit to DC, and during this, energy will be stored in the inductor. So no current will flow from a 16 ohm resistor, and the resultant circuit is shown in the figure 7. Now to get the value of I1, we will combine 4 ohm and 12 ohm resistor in parallel. And equivalent resistance will be equal to of 3 ohms. So the I1 current will be equal to source voltage divided by total resistance of the circuit, which will be equal to 2 plus 3 equals to 5, and the current I1 will be equal to of 8 amperes. Now to obtain I of t from I1, we will use current division rule, and I of t will be equal to 6 ampere for time t less than 0, or the time when switch is closed. Now we know that current through an inductor cannot change instantaneously, so the current at time t equals to 0 will be equal to current at time t less than 0 will be of 6 ampere. And this will be the initial current of the inductor. When the time t is greater than 0, the switch is open and the voltage source is disconnected from the circuit, and the resultant source-free RL circuit is shown in the figure 8. Now in the given circuit, 4 ohm and 12 ohm resistor are in series, which will give us an equivalent of 16 ohm resistance, and this 16 ohm resistor will be in parallel to another 16 ohm resistor. So both will give us an equivalent of 8 ohm resistor. Now the time constant tau will be equal to inductance divided by R equivalent and will have a value of 1 over 4 seconds. Now using equation 3, the current through an inductor will be equal to I naught exponential power minus t over tau, and substituting the values, the current through inductor will be equal to 6 into exponential power minus 4t amperes. And thanks for watching this video.